Hi, my name is Selena Yu, and I'm going to be presenting with Megan McFarland and Ranya Alkhayyat. We are undergraduates from the University of Michigan presenting our research on working memory performance under high load and distraction in order to investigate if there is a common resource for cognitive control. Working memory can be thought of as a temporary maintenance of information used to perform goal-oriented tasks. However, working memory is susceptible to task-irrelevant distractions that occur in our daily lives. For instance, if you're looking for a friend in a crowd who's wearing a red coat, you may be distracted by other red items in the environment. The ability to resist such distraction may be influenced by the availability of cognitive resources. However, it's unclear whether working memory capacity and inhibition of distraction tap into a common pool of resources. Our research tries to adjudicate between two competing accounts of how working memory capacity and regulation of distraction might interact. The first account posits that resources we use to control the impact of distraction are separate from working memory capacity. The second account posits that working memory capacity and cognitive control share a common pool of resources. We propose two alternative hypotheses. If cognitive control and working memory are separate, distraction should have the same impact on participants regardless of working memory load. Alternatively, if both use the same resources, we expect that distraction would have a greater impact at higher working memory loads.
Participants were students from the University of Michigan's introductory psychology subject pool and received credit for their participation. There were a total of 30 subjects, 18 of which were females, and all of whom had a working memory capacity of 3 or greater. Participants completed a delayed response spatial working memory task for patterns of circles. In the beginning of the trial, a varying number of circles were displayed one at a time in a 4x6 grid. Participants were instructed to keep the location of the circles active in their mind over a brief delay. After the delay, a probe, which was a question mark, was displayed in one of the squares on the grid. Participants then indicated whether or not the position of the question mark was a match or a non-match with any of the circles by pressing 1 or 2, respectively. The task was separated into 2 sessions spaced approximately 1 week apart. In session 1, we were interested in measuring individual working memory capacity. Therefore, there was no distraction and only a blank grid was displayed during the delay. They completed the task for loads 4 through 9 to ensure that they were reaching their maximum capacity. Capacity, or K, was calculated as the maximum value of throughput for each load, and throughput is the average number of items successfully recalled at each load. The equation can be found here. In session 2, participants completed the working memory task for loads below, at, and above their capacity, and with equal trials of distraction and control. In the control condition, participants viewed an empty grid during the delay. In the distractor condition, 2 circles that resembled the memoranda were displayed on a grid at the same time during the delay. Participants were told that these circles would not be displayed in any of the same positions as the memoranda for that trial.
Here on the left, you can see our results from session 1. You can see here that throughput overall asymptotes with increasing load as expected. That is, throughput increases until participants reach their maximum working memory capacity. This also highlights the importance of using a wide enough range of working memory loads. In the graph below, you can see the distribution of working memory capacity, with most of our participants having a capacity between 4 and 6. We use this information to test our subjects with a custom designed task in the second session, and the results are shown here. We can see that distraction impacts working memory performance, particularly at the highest loads. On the x-axis, we have the loads that subjects were tested at. They're tested below, at, and above their capacities. On the y-axis, we have the subject's working memory performance, based on their accuracy while performing the task. As you can see, there's an overall decrease in performance for higher loads, and an overall decrease in performance for distraction. Because our hypothesis pertains to an ordinal interaction, the appropriate analysis is a set of planned comparisons driven by theory rather than ANOVA. As you can see here, performance is especially lower for loads that exceed participants' working memory capacity, and the difference between the control and distraction conditions is significant.
As shown by the ordinal interaction, our results indicate that distractions have the highest impact when subjects have low cognitive resource ability. This finding supports the common resources account, which predicts that working memory capacity and the ability to control distraction tap into a common pool of resources. When completing working memory tasks under loads that exceed their capacity, subjects might not have enough resources to also deal with irrelevant distractors. These results advance our understanding of the roles of working memory and cognitive control. In the future, we plan to adapt the task for an fMRI experiment in order to examine the neural correlates of the interactions between working memory load and distraction. We want to thank you for your time, and if you have any further questions, feel free to reach out to our lab's email, agememorylab@gmail.com.